So in the last lesson, we looked at an example of a linear system, um, uh, and via elementary row operations, we were able to reduce that linear system to the following augmented matrix. So it was reduced to the following form: 1, -1, 1, 0, and 0, 10, 25, 90, and 0, 0, -95, -190, and 0, 0, and 0. So this form has a special name, and it's known as the row echelon form. So let me write it down. It's known as the row echelon form. All right. And all of the elementary row operations in Gauss elimination ultimately have to reduce a linear system or an augmented matrix into row echelon form. So more specifically, an augmented matrix is row echelon if let me write it down, all the non-zero rows, and which is actually rows with at least one non-zero element, Okay, so all the non-zero rows are above the rows with all zero element. So are above the rows with all zero elements, and you can see that is the case in this row echelon form reduced augmented matrix. So the fourth row is a zero row that has all the elements as 0, and all the non-zero rows, that is the first 3 rows, are above the fourth row. So you might remember that this row actually happened to be the second row, and we moved its position and moved it to the fourth position. All right. And the second condition, or the second condition for a matrix to have a row echelon form, is that the first non-zero element from left in a non-zero row, okay, and this element has also known as the pivot element, also called pivot, is strictly to the right of the first non-zero element of the row above. So what this long statement means is that, let's take an example. So the first non-zero element from left in a non-zero row, so let's consider row number 3. So the first non-zero element in row 3 is -95, right? And -95, basically this coefficient also served as the pivot element, right, or the pivot element, and this element has to be strictly to the right of the first non-zero element of all the rows above it. So it's strictly to the right of 10 here, right? So it's not directly below 10, is not on the left of 10, it's actually strictly on the right of 10. Likewise, consider 10, right? So 10 is the first non-zero element of the second row, and it served as the pivot element when we are doing Gauss elimination, and 10 is to the right of 1, which is the first non-zero element of the row above the second row. So this is like this. So 10 is not below, let's say 10 is not here, it's not here, so 10 has to be here. It's on the right of the first non-zero element of row 1, which is 1. Okay, so let's look at a few more examples to solve linear system using Gauss elimination, and I'll point out that how Gauss elimination in the end reduces an augmented matrix to the row echelon form. Okay, so let's consider a few examples. So let's consider Gauss elimination for an undetermined system. So let's consider Gauss elimination for an undetermined system. And we know what an undetermined system is, right, from the last lecture. So an undetermined system is the one where the number of equations is less than the number of unknowns. So let's consider such an example. So let's see if we can come up with such an equation. So let's say we consider 3x1 plus 2x2 plus 2x3 minus 5x4 is equal to 8. Okay, and let me actually not write it like this, because I want to actually leave some space for writing the augmented matrix also. So this is 3x1 plus 2x2 plus 2x3 minus 5x4 is equal to 8, and let's say 0.6x1 plus 1.5x2 plus 1.5x3 minus, let's say, 5.4x4 is equal to 2.7, and 1.2x1 minus 0.3x2 minus 0.3x3 plus 2.4x4 is equal to 2.1. And now you can easily write the corresponding augmented matrix, right? So this will be 3, 2, 2, minus 5, 8, and this will be 0.6, 1.5, 1.5, minus 5.4 and 2.7, and this will be 1.2 minus 0.3 minus 0.3 and 2.4 and 2.1. Okay, so now, as always, we consider the first equation as the pivot equation and the first unknown in the pivot equation as the pivot. So we got x1 as the pivot, and the goal is to eliminate x1 from all the rows below it. So we got to eliminate x1 here, and this guy is the pivot. Okay, and you can do so by applying elementary row operations. So what you can really do is that if you subtract 0.2 times the first equation minus the second equation, and if you subtract, let's say, 0.4 times the first equation from the third equation, we will be able to eliminate x1 from the second and the third equation. So let me write it down. So if you do so, you will be left with the following linear system. So this will be 3x1 plus 2x2 plus 2x3 minus 5x4 is equal to 8. And now with all the x1s gone, you are left with 1.1 x2 plus 1.1 x3 minus 4.4 x4 is equal to 1.1, and minus 1.1 x2 minus 1.1 x3 plus 4.4 x4 is equal to minus 1.1, and the corresponding augmented matrix will be 3, 2, 2, minus 5, 8, and this will, the next row will be 0 now, and 1.1, 1.1, minus 4.4 and 1.1, and again the third row will be 0, minus 1.1, minus 1.1, and 4.4 and minus 1.1. all right, now we apply the same method to row 2 and leave the first row as it is. We do not touch it now, we leave the first row as it is. So now this second equation becomes the pivot equation, and the first unknown, that is x2, this guy becomes the pivot. all right, and we got to eliminate all the x2s from the rows below. So now we just have one row below this, so we got to eliminate x2. So we are going to eliminate this guy. So let me write it down. We will eliminate this guy. Okay, and you can eliminate if you subtract this equation. If you multiply minus 1 times this equation, the second equation, and subtract it from the third equation. So if you do so, you will be left with the following linear system. So this will be 3x1 plus 2x2 plus 2x3 minus 5x4 is equal to 8, and this becomes 1.1 x2 plus 1.1 x3 minus 4.4 x4 is equal to 1.1, and you got zeros all below. 0, 0 is equal to 0, and the corresponding augmented matrix now would be 3, 2, 2, minus 5, 8. all right, and 0, 1.1, 1.1, minus 4.4 and 1.1, and zeros, all zeros below it. all right, and now you can easily find out the value. So in this case, from the second equation, right, from the second equation, this guy, we will get x2 is equal to 1 minus x3 plus 4x4. okay, and from this and this, using this equation and the first equation, you will get x1 is equal to x1 is equal to, I think this will be 2 minus x4. okay, now the interesting thing here is that I mentioned in the beginning that this is an undetermined system. What it really meant was that the number of equations were less as compared to the number of unknowns. So basically you do not have enough information about the system to arrive at a unique solution. So such a system will have a lot of solutions, in fact infinite number of solutions. So in this case, x3 and x4 remain arbitrary. okay, and for unique values of x3 and x4, we will be able to generate unique value for x2 and x1. And since x3 and x4 is free to choose any value, in fact infinite number of values, so as a result of which x1 and x2 will also have infinite number of values. And one more quick reminder, or one more quick note, why we always try to reduce a Gauss elimination into a reduced or reduce it to a row echelon form, is because it's easy to do back substitutions, right? Because what we are doing progressively is that we are getting rid of unknowns as we go down the equation, right? So as we move from the first to the second equation, we got rid of x1, so we are left with only x2, and we can compute x2 like so. And once we got x2, we can actually now compute x1. So okay, I think I'll make this point further more clear by giving you some more examples. So now let's consider Gauss elimination if a unique solution exists. So this case is a unique solution exists. Okay, and remember, if for unique solution to exist, what you need is that the system has to be determined, and for that to happen, the number of rows or the number of equations have to be equal to the number of unknowns. So let's consider one such system. So let's consider minus x1 plus x2 plus 2x3 is equal to 2. Okay, and then 3x1 minus x2 plus x3 is equal to 6, and minus x1 plus 3x2 plus 4x3 is equal to 4. And the corresponding augmented matrix would be minus 1, 1, 2, 2, and then 3, minus 1, 1, 6, and minus 1, 3, 4, 4. Okay. So as usual, again, we will consider the first equation as the pivot equation and the first unknown here as the pivot. So this guy becomes pivot, and we are going to eliminate pivot, that is x1, from all the rows below it. So we got to eliminate x1 from row 2 and row 3. And to do that, what you got to do is that you can multiply the first equation by 3 and add it to the second equation to get rid of x1 here. And you can also subtract row 3 from row 1 to get rid of the x1 element here in row 3. And if you do so, you will be left with a new linear system, with a linear system which will have the same solution as the previous linear system, and this will be minus x1 plus x2 plus 2x3 is equal to 2. And now with the x1s gone, we got 2x2 plus 7x3 is equal to 12, and 2x2 plus 2x3 is equal to 2, right? And let's write the augmented matrix here. So it's minus 1, 1, 2, 2, and now this guy, so here it will be zeros, right, because we have gotten rid of all the x1s. So 0, 0, and then this will be 2, 7, 12, and this will be 2, 2, 2. Okay. Now further, let's now, using the same logic, right, now we will leave this equation untouched. So this, we are done with this guy, the first equation. Now moving on to the second equation. The second equation becomes the pivot equation, and the first element of the pivot equation, that is in row 2 or equation 2, is x2. So this guy becomes pivot, and we got to get rid of x2s or the pivots from all the equations and rows below it. So there is only one equation, that is row 3. So this x2 has to be eliminated. So we will eliminate this guy. Eliminate this guy. So, and you can do this by just subtracting row 3 from row 2. So now if you do so, you will be left with the following linear system. It will be minus x1 plus x2 plus 2x3 is equal to 2, and this becomes 2x2 plus 7x3 is equal to 12, and this becomes, the third row becomes minus 5x3 is equal to minus 10, and the corresponding augmented matrix here would be minus 1, 1, 2, 2, and this becomes 0, 2, 7, 12, and this third row becomes 0, 0, minus 5, minus 10. So now you can look at the beauty of Gauss elimination and why we are actually making it reduced to row echelon form. So if you work backwards now, if you're going to work backwards now, here we just have to solve for x3. Okay, so if you solve for x3, x3 is equal to 2. Using this value x3 here, you can substitute the value of x3 in the row above here, and you will get x2 is equal to minus 1. And now using the values of x2 and x3 thus obtained, you can now compute the value of x1, and you will see that x1 is equal to 1. So in this case, we do see that the system has a unique solution. Finally, let me also give you an example where a linear system has got no solution. And let me write down such a system first. So, okay, so let's consider such a system. So let's say we have the following linear system: 3x1 plus 2x2 plus x3 is equal to 3, and let's say 2x1 plus x2 plus x3 is equal to 0, and 6x1 plus 2x2 plus 4x3 is equal to 6. All right, and the corresponding augmented matrix would be 3, 2, 1, 3, 3, 2, 1, 3, and 2, 1, 1, 0, and 6, 2, 4, 6, 6, 2, 4, 6. Okay, so as usual, again, consider the first row as the pivot equation and the first element or the first unknown as the pivot. So this guy is pivot, and we are going to eliminate the pivot, that is the x1, from all the rows below it. So we are going to eliminate these two elements here, and the way to do that would be by subtracting 2 by 3 times the first equation, right? By subtracting 2 by 3 times the first equation from the second equation, and 6 by 3, that is equal to 2 times the first equation from the third equation. All right, and this will give you the following system. So this will give me 3x1 plus 2x2 plus x3 is equal to 3, and minus 1 by 3 x2, x1s are gone now, plus 1 by 3 x3 is equal to minus 2, and minus 2 x2 plus 2 x3 is equal to 0, and the corresponding augmented matrix would be 3, 2, 1, 3, 0, minus 1 by 3, and then this will be 1 by 3 and minus 2, and this will be 0, minus 2, 2, 0. All right, now I think you already have a hang of this, and you will know what I'm going to say next. We are going to forget this first equation, move our focus to the second equation or the second row. The first unknown in the second equation is x2, and this guy becomes the pivot, and we are going to eliminate x2 from all the rows or all the equations below this. So we got to eliminate this guy, minus 2x2. Okay, and you can do it by subtracting 6 times the second equation from the third equation. So anyways, let me just quickly write down the resultant linear system. So this will be 3x1 plus 2x2 plus x3 is equal to 3, and minus 1 by 3 x2 plus 1 by 3 x3 is equal to minus 2, and something surprising happens. So 0 is equal to 12. Let me write down the corresponding augmented matrix also. So this is 3, 2, 1, 3. The second row is 0, minus 1 by 3, 1 by 3, and minus 2. And this guy is 0, 0, 0, and 12. And what is surprising is that the last row, the third row, it says 0 is equal to 12. But this is not possible. This statement or this equation is contradictory. So hence, this linear system has got no solution. Really got no solution. Okay. So what we have seen till now is that the Gauss elimination process can be used for any kind of linear system, when it has a unique solution, when it has infinite number of solutions, or when it has got no solution. All right. So just to generalize stuff now. So basically, at the end of the Gauss elimination, the reduced linear system will have the following form. Okay, so let me write it down. General form: a11 x1 plus a12 x2 plus dot 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 plus a1n xn is equal to b1. And then we will have c22 x2 plus dot 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 plus c2n xn is equal to b1, let's say tilde. And remember, these coefficients will be different, right? Because we always left the first equation untouched, and we use the first unknown, that is x1 in this case, to eliminate x1 in all the rows below it. So in all the rows below the first equation, you will not find x1 terms at all, and the coefficient for rest of the unknowns will be changed, right? Because you must have added, subtracted the first equation to the second, third, fourth, and let's say till the mth equation. So hence the coefficient for all the subsequent coefficient for the unknowns in the subsequent equations will change now. Okay, and so on and so forth. So k, let's say r xr plus dot 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 plus k r n xn is equal to br. And then we have, let's say, 0 is equal to br plus 1, 0 is equal to br plus 2, and so on and so forth till 0 is equal to bm. So we have considered a linear system which had n unknowns and had m equations. Okay. So from this, with respect to our solutions, there are three possibilities. Okay. So there are three possibilities, and we have covered these three possibilities as the examples also earlier. So there is no solution. There is no solution if r is less than m and one of let's say br plus 1 or any one of br plus 1, br plus 2, or bm, let me do the tilde here, is not 0. Is not 0. And this is the example, and this is the example that we saw in the last case. So in this case, right, we arrived at this case where 0 is equal to 12, so there is no solution. The other thing that we can do, or the other case that we need to consider, is that there will be precisely one solution or a unique solution. There will be one solution or unique solution if r is equal to n and br plus 1 and br plus 1 or br plus 2 or so on and so forth till bm, if at all they are present, these guys, if they are present, they are 0. So are all zeros. So this is the case for a unique solution, and and the third case is infinite number of solutions. So the third case is infinite number of solutions, and this is the case if R is less than n and BR plus 1 or BR plus 2 if present till BM, if they are present, they are all zero. Okay, so I think this is too much to digest or too much to understand in one lecture, so I'll actually urge or request you to maybe rewatch this lesson again and look at all the examples, and I'll see you guys in the next lecture.